Topic 3.3 Standard Test Methods and Interpretation. On the fatigue SN test, from the picture over here is the engineering component that's subject to fatigue loading, comprising the camshaft, the connecting rod, and also the pistons. And in the middle here is the camshaft before putting into the service. However, during service under fatigue loading, unfortunately, it failed, showing the fractured surfaces like this, as you can see in this picture. And for the fatigue failure, it is typical that you can see very unique characteristic on the surface. And it's very unique that you can find the benchmark on the fatigue surface like this. And by looking at this benchmark, it will finally lead to the initiation of the fatigue crack, which we can see as the big porosity here. Another example of the fatigue failure that you can see in the aerospace area. The aircraft is subject to many types of loadings. For example, in the fuselage, it will be subject to pressurized and depressurized when taking off up to the high level and then coming down to the ground stage. Other than that, the wing that is also subject to compressive and tensile strength according to the vibration, according to the pressure on the top and the bottom of the wings during taking off and landing. And hence for a long period of time in service, this might cause the fatigue failure as you can see from this picture. Once again, you can see the benchmark pointing to one fatigue initiation site. And the last example, here's the train wheel that is subject to fatigue during service as well. The weight of the train putting on the train wheels against the rail will produce the cyclic loading and unfortunately will fail under fatigue, as you can see from the picture over here. And from these three examples, you will see something in common, which is the fracture surfaces are flat with no gross plastic deformation. And also we can see the benchmark by our naked eyes. The flat surface showing less deformation and brittle type of fracture. So the fatigue failure is considered to be quite dangerous and need to study in more detail. The fatigue failure accounts for over 90% of all service failures due to mechanical causes. And it occurs when the metal is subject to a fluctuating stress or the cyclic stress and will fail at a stress much lower than its tensile strength. Imagine if the metal has a tensile strength of 1000 megapascal. But when working under the fatigue loading, it might fail at the fatigue of just 500 megapascal. That is for example. And the fatigue failure occurs without any plastic deformation or no warning, so it is dangerous. And the fatigue surface appears at a smooth region showing benchmark leading to the origin of the fatigue crack. I'm giving here showing the example of very clear benchmark that we can find on the fatigue surface. The conchoidal nature of the benchmark will give the direction to the origin of the fatigue crack. And if we work backwards, we can see that once the fatigue crack originates over here, the crack will advance towards the cross-section of the component until reaching the critical fatigue length over here. At this stage, the rest of the cross-section cannot bear the fatigue load anymore, and that will cause overload and fail under fatigue. Here is another example of the fatigue crack origin in a test specimen of 4040 steel having the ultimate tensile strength of 780 megapascal. But the sample failed at the alternating stress at 440 megapascal. Under the investigation using scanning electron microscope, or SEM, we can see that the origin of the fatigue crack is locating over here. And once we look closer, we can see that this point might be the cause of failure. And when we enlarge this area at a higher magnification, we can see the inclusions. This is the possible fatigue crack nucleation site that is sitting right next to the sample surface. The source of cyclic loading can come from many types and is different from the static load, which is stable and continuously present. Therefore, the source of cyclic loading can be from the working load, and this is due to the function that it performs, like the rotating motion of the turbine blade. For example, Another one is the vibratory load that will come with high frequency but low amplitude of stress. For example, when the machine is working, that will produce little vibration onto the machine itself as well. And the last one is the accidental load, which is quite rare and unusual conditions. And this type of loading causes overloading, having high stress amplitude that will cause the final failure. I'm giving you the example in the picture on your right hand side here is the loading cycles on one flight of a fixed wing aircraft, showing variations of the cyclic loading with time. First, if you look over here, during landing and then taxiing of the airplane, that will produce small amplitude of loading. And once the airplane taking off, the load increases until reaching the maneuver stage. Then the flight is going on little vibration over here. However, in the incident of the storm coming, the amplitude of the cyclic load is huge over here, and then can come back to small variation when the flight can maneuver again. Once the airplane is going to landing, the load comes down and keep a little vibration down here during taxiing, and it happens like this. And you can see that the loading cycle is not in a systematic pattern. Then we can transform this into a more simplified version of the loading by looking into picture B. From over here, taxiing can be in a small amplitude and maybe over 2000 cycles. And once the airplane is taking off, over the maneuvering of the plane, going to small vibration over here, and then when the airplane maneuver, it will go through approximately 200,000 cycles of stress. And if the airplane experiencing the storm, the amplitude of the stress will be larger and larger like this. We can also count the number of cycles that the airplane experiencing. To this, the information now is more simple and very useful. So the actual cyclic loading is normally complicated, and it is better to give the simplified cyclic loading in order to extract the information for the determination of fatigue performance of the component, which I will tell you. And that we follow the ASTM E466-15. And again, you can download it online. And before we go into the determination of the fatigue performance, now I would like to introduce you the nomenclature of the fatigue parameters. As you can see from this graphical demonstration, we have here in the x-axis is the time or cycles of fatigue, and along the y-axis here is the stress. And remember, the tensile stress is positive and the compressive stress is in negative values. Over here, I introduced you the fatigue cycle in the most simple form of the sine curve. The first parameter that you have to get familiar with is the maximum stress, that is the values on the top of the sine curve over here. And so the minimum stress gonna be at the bottom of the curve. And next is the mean stress, which is the average values of the maximum and the minimum stresses. Whereas the delta stress or the stress range can be found as the difference between the maximum stress and the minimum stress. And finally, the stress amplitude or the alternating stress is half of the stress range. And therefore, for summary, we now have the parameters as follows: the maximum stress or sigma max, the minimum stress or sigma min. Then we have the stress range, and you can write as the delta stress or sigma r that equals sigma max minus sigma min. And then is the alternating stress or the stress amplitude or sigma A, which is half of the stress range. And next is the mean stress or sigma M, which is the average values of the sigma max and sigma min. And lastly, the stress ratio or R, that is the ratio of the sigma min to sigma max. All the parameters are very important that you have to refer to every time you perform the fatigue test. And if you look on the fracture surfaces of the specimen felt under fatigue in the stage 2 of crack propagation, it normally shows a pattern of ripples of fatigue striations, as you can see from this picture. This is a special feature that you cannot find from any type of failure apart from fatigue. This type of feature is very unique and you can find it just only from the component that are under fatigue. If you remember the feature like fish mark that we can see on the fatigue surface by naked eyes, but the fatigue striations are different. They are very small and we need the scanning electron microscope for the investigation. The fatigue striation shows how fast the fatigue crack will grow and also the direction of the fatigue crack. And from this picture, we can see that the fatigue crack direction is normal to the fatigue striation. That means the fatigue crack advances from the left to the right. Each striation is produced by a single stress cycle. And what does it mean by a single stress cycle? I'm introducing you here the stress cycle, which will start it from here, going up, down again, and back to where it started over here. And this is a single stress cycle. And I will tell you how the striation is related to the stress cycle. First, looking at the cross-section of the fatigue crack over here. Over here is the upper crack surface. So, down here is the lower crack surface. At the start, we have 1, 2, 3, 4. So, there are 4 striations at the first start. Over here, we can see that the metal is subject to a minimum load, that the crack is in the closed position, which is along here at the bottom of the curve. And once the load is increasing along the red line, the crack is now opening. And there are some slit planes operating at the tips of the striation. And further, once the load is increasing, approaching the maximum load over here. Now, the crack at maximum load is blunted and advanced forward to another step like this. When the load is going down, the crack is now closing. The slit then acting in the opposite direction. And finally, we come to the closed state of the crack when the load is coming down to the minimum level of load back to where it started. And now over here, at the 5th step of the fatigue striation, we now have 1, 2, 3, 4, 5 striations, which is 1 striation more than one that we have started. So I hope that you understand the nature of fatigue a little bit more. Then let's move on to how to perform the fatigue test. Up here showing the specimen's dimension with the continuous radius between ends of the specimen. And over here is the diameter of the test sample. And this can be done according to ASTM E466. Down here is a simple version of the fatigue test. Once we secured the specimen onto the machine, one end of the sample is attached to the motor that is driving the shaft here in a rotating motion. Once we put on the weight, that will produce the stress acting on the specimen. And once we start the testing, the motor will drive the shaft to rotate the specimen until it fails under different level of stress, which is the weight or the load put on. The revolution counter here is used to count the number of cycles to failure. And as the rule, when we put on more weight, there will be less number of cycles to failure that the specimen will stand. And if you look a bit closer over here, you can see that once the sample is subject to fatigue, the volume of specimen on the top is subject to tensile loading, whereas one underneath here is subject to compressive. And once it's moving up, one that was subject to tensile now will be subject to the compressive stress. And this is how we call the completely reverse cyclic loading. So for summary, under the cyclic loading, the specimen is subject to tensile and compressive loading alternately. And by varying the load or the stress, the number of cycles to failure will be counted and then plot as the SN curve. And S is for the stress, N is for the number of cycles to failure. As you can see over here, the number of cycles to failure or N is plotted on the x-axis. And you can notice that it's in the log scale because the number of cycles to failure is huge, that the specimen can fail at 1,000,000 cycles over here. And for the stress, on the y-axis is plotted on the normal scale in megapascal. From the data, there are 2 types of methods test under fatigue. The first one is the mild steel that shows the fatigue limit. Another type is the non-ferrous metal, which is the aluminum alloy, however, do not show the fatigue limit, and its graphs coming down. For the fatigue test, as the stress level increases, the number of cycles to failure will decrease. And for the ferrous metal like mild steel and cast iron, It's easy to find the fatigue limit over here, but for non-ferrous metal like aluminum or magnesium alloys, it is difficult to find the fatigue limit, and normally it will be designed at some number of cycles to failure, for example, at 10 to the 8 cycles to failure. And for the determination of fatigue limit or the endurance fatigue limit, it is the fatigue stress that will not cause failure. And for safety, the working stress has to be lesser than the fatigue limit. And by looking at this example, for the determination of fatigue limit, similar to the last SN curves, we have over here the steel samples tested on the high cyclic stress level. As you can refer to the y-axis on the right-hand side. And once we're reducing the stress level, the number of cycles increases until reaching to the level that the specimen will not fail any longer. And to find out the endurance limit or the fatigue limit, we just go across to find the stress level to the left, or we can refer the stress level to the axis on the right as it is in the megapascal. To this, then we'll have the endurance limit of 300 megapascal. And therefore, for the safety reason, the working stress is designed under the level of fatigue strength. Over here are some examples of the fatigue strength in relation to the ultimate tensile strength. First, for ferrous metals such as steels and cast iron, the fatigue strength, which is sigma E, may be approximate to half of maximum tensile strength. But for the non-ferrous metals, for example, aluminum and magnesium alloys, this type of metals do not show the fatigue limit, and therefore it is defined at approximately 10 to the 8 cycles to failure, and is normally less than 1/3 of the maximum tensile strength. So think carefully when you choose the non-ferrous metal to work under fatigue. There are several factors that affect the fatigue performance of the metallic components. First, the nature of cyclic loading, which are stress amplitude, mean stress, or the stress range, for example. Second, the surface quality, which are roughness, residual stress, and surface treatment. Next is the metallurgical discontinuity, that we have to look deeper into the microstructure, whether it's coarse or refined microstructure. Maybe there's some inclusions or defects that will introduce the weakness to the component. And for the first factor on the nature of cyclic loading, such as stress amplitude and mean stress, and we can see that as the cyclic stress increases, the fatigue life decreases. But on the other hand, if the cyclic stress reduces, the fatigue life increases, as you can see from this SN curve over here. Up there, the stress amplitude, and the stress amplitude is huge. Therefore, it is more dangerous for the metallic part to be subject to, and then causing a shorter life. That you can relate from the graph over here. At high stress level, that causing short fatigue life. But then, if we reduce the stress amplitude to be small like this, the small stress amplitude then is not as dangerous as the bigger ones. Hence, when we lower down the stress level, we can now have the metallic component working at a longer life. Another factors that affect the fatigue performance, and this is very important in the state of component production, is the surface quality. That can be the roughness of the surface, the residual stress remain on the surface, and also the surface treatment that apply onto the specimen. Over here you can see 3 specimens with different surface finishes. The first one on the right is the specimen having the machined surface, so you can see it as looking quite bright over here. If you have a look onto this graph over here, showing the relationship of the fatigue strength with the maximum depth of roughness, it means that the greater the values of the depth of roughness, the rougher the specimen surface is. Therefore, when we have a smooth surface over here, either it's going to be the spring steel that has been tempered, that you can see from the green lines over here, or the chromium molybdenum steel that has been tempered, both possess high fatigue strength. And for the medium carbon steel that has been annealed, that of course for this type of steel has a lower tensile strength, and hence it will give lower fatigue strength as well. So this means that if you want the metallic component to withstand higher fatigue strength, you have to choose the one that gives you the higher tensile strength as well. It's normally giving the same strength. And as we're going through the right of the x-axis, the specimen surface becomes rougher, and that will give like very small defects onto the specimen surface. And that small defect can act as a fatigue crack initiating on the surface. And that will eventually cause the fatigue failure and shorter life of the specimen. As you can see that the curve is coming down for all the three samples. So the smoother the surface is, the greater the fatigue life. Another factor is the residual stress. I have to mention that there are two types of residual stresses. One is tensile residual stress, and another is compressive residual stress. What you have to keep in mind that we only need the compressive residual stress on the metal surface. It is the negative values. Therefore, in order that the specimen will fail under fatigue, it has to withstand a greater fatigue stress putting on its surface. Therefore, the greater the compressive surface, the greater fatigue life the specimen will obtain. And another factor that affecting fatigue performance is the surface treatment. As you can see from these two specimens that have been experienced surface treatments, the first one is nitriding process and another one is carbonitriding. The two treatments are known to give better hardness onto the metal component surface. And it's good because this type of surfaces will prolong the fatigue crack initiation, and this will give a longer fatigue life. And the last fact that I will give you here is the metallurgical discontinuity. As you have learned from the start of the course, all the mechanical properties are related to the microstructures of the metallic parts. The refined microstructure will of course offer the greater strength to the metallic parts, and that will also give a higher fatigue strength and the longer fatigue life. The coarse grain or coarse microstructure is therefore have to be avoided. Inclusions and defects are not desirable as well, as this gives discontinuity to the microstructure of the metal component. As you can see from the example over here, the failure of the camshaft that originated at this huge porosity that might be from the casting process. The large porosity of course cannot bear the stress and act as the weakest link that caused the final fatigue failure. And to the right, I introduced you again with the initiation of the fatigue crack. That the inclusion was found on the fatigue fracture surfaces, and the location of this inclusion is right next to the surface of the specimen. So remember, the surface of the component is very important for fatigue performance. It has to be smooth, having high hardness and strength with good uniform and refined microstructure without inclusions or defects. Lastly, I'm giving you the case study for fatigue failure in engineering components, and this is for the connecting rod. Earlier, the part that you're looking at is the camshaft over here, and the connecting rod connect camshaft to the piston. In this case, the connecting rod undergoes cyclic loading under tensile and compressive during the combustion cycle, and it suggested the fatigue could be the cause of failure. By looking at this investigation, showing the diagram of an example connecting rod with key features, here is the connecting rod shank, the small end that is connecting to the piston, the big end over here, the bolt housing, the slip bearing that is surface housing the camshaft. The fatigue failure of the connecting rod can be found from different locations. To investigate the root cause of the fatigue failure, it was found that the presence of the scale build-up inclusions which lead to microcracking during fatigue loading of the component. That means once this component is in service, that's of course experience the fatigue loading. And unfortunately, at high service temperature during the combustion cycles, the scale building up and the inclusion will act as the fatigue initiation site. More investigation on the fatigue surface, we can notice the origin of the fatigue crack over here, and this picture on the right can see at a higher magnification, as you can see by the pointing direction of the red arrow. To get it a closer look, then we have to study the fatigue fracture surface under SEM. And we can see that on the fatigue crack origin, then notice the sulfide-rich inclusion over here on the surface. The red arrows giving the direction of the fatigue crack advancing towards the component section. With the help of FEM analysis, as you can see from the pictures here, we can simulate the stress condition on the whole component of the connecting rod. From this, it confirms the location of the crack over here in figure D, that the location of the crack corresponding to the maximum stress of 300 megapascal matches the fracture location locating between the big ends and the shank, like you can see over here from the picture on the left-hand side. So this is how we investigate the fatigue failures in engineering components. Although it's unfortunate that this fatigue failure happened, but it is necessary to investigate to see the root cause of the fatigue failure in order that we can fix it by looking at where it started. And once we found out the cause of it, then we can either change the design or be careful about the metal processing of the component with refined microstructure and without inclusions or defects that can be the weakest link for fatigue crack initiation.